Good evening. Settle in, get comfortable, and prepare for a journey to the very edge of our understanding. What if I told you there's something in the universe capable of moving faster than light? Something that defies the most famous law of physics, established by Albert Einstein every single day. Sounds like science fiction, doesn't it? But this is reality. Tonight, in our sleep lecture, we are going to dive deep into one of the cosmos' most beautiful and deceptive mysteries, the enigma of the cosmic shadow. And by the end of this journey, you will understand exactly how you can outrun light without breaking a single rule. Now, what do you think this shadow is? Share your initial guesses in the comments below before we begin our deep dive. Let's get started. Before we set off in pursuit of this shadow, let's lay the groundwork. In the early 20th century, Albert Einstein gave the world his special theory of relativity. One of its fundamental postulates stated that the speed of light in a vacuum is a constant, roughly 300,000 kilometers per second. And it's not just very fast, it is the absolute speed limit for anything that possesses mass and carries information. Why? Imagine you're trying to accelerate a spacecraft. The closer its speed gets to the speed of light, the more energy you need for any further acceleration. To actually reach the speed of light, you would require infinite energy. The universe is essentially telling us this barrier is insurmountable. This principle became the cornerstone of modern physics. It dictates causality, the relationship between cause and effect, and the very structure of space-time itself. Any violation of this law would lead to paradoxes where the effect could occur before the cause. So, how does this shadow manage to circumvent this universal law? Let's begin with the most basic question. What exactly is a shadow? We instinctively see it as some kind of dark object constantly trailing us, but from a physics perspective, a shadow is not an object at all. It is simply a region of space where light is blocked by an obstruction. A shadow is the absence of photons. It possesses no mass, holds no energy, and has neither density nor temperature. It is purely an informational zero, a void in the flow of light. To illustrate this, imagine a room with 100 light bulbs on the ceiling. If you switch just one of them off, a dark spot appears on the floor. If you then turn them off sequentially, that spot will appear to move. But is anything material actually moving? No. What is moving is only the boundary between light and the absence of light. This is the crucial concept that unlocks the entire mystery. A shadow is not a thing, it is an effect. It doesn't obey the same rules as physical objects because, fundamentally, it is not a physical object itself. Let's run a quick thought experiment to clearly illustrate how a light spot, or even a shadow, can appear to move faster than the speed of light. Imagine yourself standing in the dead center of an enormous circular room. The walls of this room are located a distance of, say, 1 light-year away from where you stand. You're holding a powerful laser pointer, aiming the beam at the wall where it creates a single bright spot. Now, perform a very simple action. Slightly flick your wrist, just 1 single degree. What happens to the light spot on the far wall? It instantaneously sweeps across an arc. Let's calculate the distance this spot just traveled. The circumference of a circle with a 1 light-year radius is immense. Even that tiny angular shift will force the light dot to cover a colossal linear distance along the wall. If you flick your wrist quickly enough, say in 1/100th of a second, the linear speed of that spot moving across the wall will vastly exceed the speed of light. But does this violate the fundamental laws of physics? Absolutely not. This is because the photons that illuminate the wall at point A are completely different from the photons that illuminate the wall at point B. There was no actual object or information whatsoever traveling faster than the speed of light. Now let's look at how this same principle applies to shadows, but in reverse. Imagine the exact same scenario but slightly different. Instead of holding a flashlight, you are the light source, like a bare light bulb, and you hold your finger right in front of you. The shadow of your finger falls onto that same distant wall located 1 light year away. This shadow will be absolutely gigantic. Now you make the exact same movement, you slightly pivot your finger. The shadow on the wall will instantly sweep from one point to another. And again, because of the vast distance and the laws of geometry, the linear speed of that shadow's movement can be arbitrarily fast. It could exceed the speed of light by thousands or even millions of times. Yet again, this involves no violation of the laws of physics. Why? Because a shadow is merely the absence of light. At point A, the light stops being blocked, and simultaneously at point B, it starts being blocked. These two distinct events are not directly connected. The information about your finger's movement reached different sections of the wall at the speed of light, but the boundary of the shadow itself formally moved faster. Let's take this thought experiment and apply it to the cosmos itself. The universe provides the ideal conditions for observing this phenomenon. All we need is a light source, an obstacle, and an incredibly distant screen. The light source could be any star or even an entire galaxy. The screen can be giant clouds of interstellar gas and dust, nebulae stretching across countless light years. What serves as the obstacle? Essentially anything situated between the source and the screen, a planet, another star, or even a black hole. But the most fascinating drivers of superluminal shadows are pulsars. These incredible objects are perfectly suited for our task. They spin at tremendous speeds, creating the effect of a cosmic lighthouse. It is through them that we can actually see a shadow racing across the cosmic expanse, literally outpacing light. So, what exactly is a pulsar? Picture a star significantly more massive than our own sun. Towards the end of its life, it explodes in a brilliant supernova. What remains after this spectacular event is an incredibly dense core. This object is what we call a neutron star. Its matter is so compressed that a single teaspoon of it would weigh billions of tons. Some of these neutron stars have incredibly powerful magnetic fields. They shoot out narrow beams of radiation, including both radio waves and visible light, from their magnetic poles. Meanwhile, the star itself is spinning incredibly fast, sometimes completing hundreds of rotations every single second. The resulting beam sweeps across the cosmos, much like the beam of a lighthouse. If Earth happens to be in the path of that beam, we detect periodic flashes. This is precisely why they earned the name pulsars. For the purposes of our experiment, a pulsar is the perfect spinning obstacle, or, to be more precise, the ideal light source for creating a moving shadow. Now let's put all the components together. We have a pulsar spinning, let's say, 10 times per second. It emits a narrow beam of light. Thousands of light years away, at a vast distance, sits a giant cloud of gas and dust. This is our screen. The pulsar's beam sweeps across this cloud, illuminating it and creating a moving point of light. The speed of this point, as we established during our earlier thought experiment with the laser, can vastly exceed the speed of light. Now, imagine there is another object located between the pulsar and the cloud, for example, a small, dense dust cloud. This cloud would block the pulsar's beam. In that case, what races across the giant screen of the distant nebula is no longer a bright spot but a shadow, and the speed of this shadow would be exactly the same, superluminal. Astronomers actually observe phenomena just like this. They witness patterns of light and shadows cast by pulsars sweeping across distant nebulae, and the calculated speed of these movements is truly staggering. To truly grasp the scale, let's look at a concrete example. Take the famous Crab Nebula pulsar. It spins at a staggering rate of about 30 times per second. The nebula itself, which serves as our cosmic screen, is located several light years away from the pulsar. Simple math reveals that the shadows and light spots created by the pulsar on the nebula material are moving at velocities roughly 500 times the speed of light. Just try to imagine that. By the time a single photon of light leaves the pulsar and finally reaches the nebula, the corresponding shadow on the nebula will have circled the material hundreds of times. It's essentially a giant cosmic movie theater where the projector is spinning so rapidly that the image on the screen travels faster than the light emanating from the projector. This is one of those phenomena that truly forces us to reconsider the familiar laws of physics and recognize just how astonishingly counterintuitive the universe can be. The crucial question here is, can we harness this phenomenon to transmit information faster than the speed of light? Could we, for example, send superluminal telegrams simply by manipulating a shadow? Unfortunately, the answer is no, and this refusal is the key to understanding why the theory of relativity remains intact. Imagine you wanted to transmit a message from point A to point B on a distant screen using a shadow. To achieve this, you would need to modulate the shadow in some way, for example, by making it appear and disappear to convey Morse code. To create a shadow at point A, you must place an obstacle in the path of the light beam directed at that specific spot. Crucially, the information about you setting up that obstruction can only travel to the screen at the speed of light. Similarly, to create a shadow at point B, you must intervene directly with the light beam traveling to point B. There is no causal link between the appearance of the shadow at point A and the appearance of the shadow at point B. You cannot create a shadow at point A and somehow make it fly across the screen to point B, thereby transmitting information instantaneously. In physics, we talk about two different types of velocity, phase velocity and group velocity. To understand this, imagine waves on water. The crests of those waves move at what is called the phase velocity. However, the actual energy carried by the wave, its main bulk, travels at a different rate, the group velocity. Crucially, it is the group velocity that cannot exceed the speed of light, because it is directly related to the transmission of energy and information. The apparent superluminal speed of a shadow is a classic illustration of phase velocity. This is the speed at which an abstract front or boundary moves, but it doesn't represent the movement of any physical object. Another great example of phase velocity involves ocean waves hitting the shore at an angle. The point where the wave breaks can race along the beach at tremendous speed, possibly even faster than the waves themselves are moving out in the ocean. But obviously, no actual mass of water is traveling down the beach at that rate. It is purely a geometric effect. The situation with a shadow is exactly the same. This is how the paradox is resolved, and it's quite elegant. A shadow can move faster than light precisely because it is not a material object and doesn't transfer information or energy. Its movement is actually an illusion, a sequence of independent obscuration events happening at different points in space. Every single one of these events adheres strictly to the laws of physics and occurs no faster than the information from the light source, and the obstacle can reach that specific point. Einstein's theory of relativity remains absolutely sound. The cosmic speed limit is still fully in force, but understanding this fact doesn't make the phenomenon any less astounding. Quite the opposite, it simply adds a layer of genuine depth. We see how simple laws of geometry, when magnified across cosmic scales, can generate phenomena that appear to us as impossible, even magical. It reminds us that the universe is full of clever illusions, and our task as researchers is to learn how to distinguish them from cold, hard reality. We see similar effects pop up in other fields of physics. Take quantum mechanics, for instance, where we have the phenomenon of quantum entanglement, what Einstein famously dubbed spooky action at a distance. Two entangled particles, separated by any distance, behave as a single entity. Measuring the property of one particle instantly determines the property of the other. It seems as if information is being transmitted instantaneously, faster than the speed of light. Yet even here there is no actual violation of causality. It is impossible to use this effect to transmit meaningful information faster than light. You cannot control the outcome of the measurement you receive, which means you cannot use it to create a superluminal telegraph. Just like the shadow example, this is a stunning counterintuitive phenomenon. Nevertheless, it fits perfectly within the framework of existing physical laws, even as it forces us to deeply reconsider the fundamental nature of reality itself. Let's return to the concept of the shadow and consider alternative scenarios. What if the light source wasn't a pulsar, but something far more dramatic, like a supernova explosion? This immense event unleashes a tremendous amount of light, spreading outward in every direction, forming a spherical light front. If a dust cloud happens to lie in the path of this light, a dramatic light echo will begin to traverse its surface. Now imagine if there are other, smaller and denser objects positioned between the explosion and the dust cloud. These objects will cast their shadows onto that expanding light sphere. These shadows won't just move, they will expand and distort wildly, painting truly fantastic cosmic visuals. By monitoring the movement of these celestial shadows, astronomers can glean vital information about the three-dimensional structure of interstellar space, a region that usually appears vast, empty, and transparent. The shadow in this way transforms from a mere curiosity or paradox into a powerful diagnostic tool for mapping and exploring the cosmos. Let's look at another powerful thought experiment, the giant cosmic scissors. Imagine giant cosmic scissors whose blades stretch across light years. As you begin to close them, the point where the blades intersect starts to move. And the closer the blades get, the faster that intersection point travels. In the very last instant, right before they fully close, its speed can approach infinity. Again, this is purely a geometrical effect. The point of intersection is not a physical object, it's a mathematical abstraction. It carries no energy whatsoever. No physical part of the blades themselves ever moves faster than the speed of light. This example is highly analogous to the shadow effect because it also demonstrates how the movement of an abstract point or boundary can formally exceed the speed of light without creating a physical paradox. The universe is full of these kinds of traps for our intuitive perception, which was honed only in a world of slow speeds and small distances. Can we really consider a shadow a form of information? Well, in a way, yes. The simple fact that a shadow appears tells us there's an obstacle blocking the light source, but this is information in the most passive sense possible. The shadow itself holds no new message, can't tell us anything novel. All the data concerning the obstruction is already encoded within the light flow or the lack thereof, and travels along with that light. This is why when we assert that information cannot travel faster than light, we are specifically referring to active new information, a deliberate message that can be generated, transmitted, and received. A shadow, however, is merely a consequence of events that have already taken place. Its apparent movement across a surface is just the deployment of that pre-existing information through space and time, and crucially, this unfolding happens at a speed that never exceeds the speed of light for any specific point on the screen. This phenomenon forces us to rethink the very nature of movement. What do we truly mean when we say something is moving? Typically, we imagine an object traveling from point A to point B while maintaining its structural integrity. But the movement of a shadow is something entirely different. It's more akin to the stadium wave, where spectators stand up and sit down in sequence. The wave races through the stands, yet every single person remains in their seat. Only the pattern, the form, is moving. It's exactly the same with a shadow. No physical substance is actually being relocated. Only the boundary, created by local events, is moving. Grasping this distinction between the movement of an object and the movement of a mere pattern is the key to resolving many physical paradoxes. This applies not only to issues concerning the speed of light, but also to far more complex areas of science. But what about black holes? Can they cast superluminal shadows? The answer is definitely yes. A black hole is the perfect obstruction for light. Its shadow is the region from which light cannot escape, delineated by the event horizon. When a rotating black hole is situated next to a bright light source, like an accretion disk, its shadow, projected onto distant cosmic objects, can also appear to travel faster than light. Furthermore, analyzing the shape and dynamics of a black hole's shadow is one of the only direct methods we have to test general relativity under extreme conditions. The image of the shadow of the M87 black hole, captured by the Event Horizon Telescope, stands as one of the greatest scientific breakthroughs of the past few years. Interestingly, the concept of faster-than-light motion doesn't only pop up when we talk about shadows. In cosmology, for example, the expansion of the universe causes distant galaxies to move away from us at speeds that actually exceed the speed of light. Crucially, this does not mean they are moving through space faster than light. Instead, it is the space itself between us and them that is stretching. As a result, the light they emit can never actually reach us. They are forever receding beyond our cosmological horizon. And once more, this doesn't violate the theory of relativity, because we are talking about the movement of space itself, not objects moving within that space. It's just another perfect example of how the universe, when viewed on the larger scales, behaves completely differently from what we are used to. Let's return to our guided sleep reflection. The very fact that we can lie here, safe and comfortable, contemplating such grand and abstract concepts is truly a marvel. We, creatures dwelling on a tiny planet orbiting an average star, have somehow learned to grasp the fundamental laws that govern the universe. We can mentally journey billions of light years away, imagining shadows racing across nebulae at speeds hundreds of times faster than the speed of light. This process of knowing, this expansion of our consciousness to the scale of the cosmos, is both calming and deeply mesmerizing. It reminds us that even the darkest, most elusive concepts, like a mere shadow, can conceal astonishing beauty and profound hidden meaning. The phenomenon of the superluminal shadow is a perfect metaphor. Sometimes in life we encounter events that feel utterly impossible, as if they are breaking every rule we know. We watch as the shadow of some major event flashes across our lives with unbelievable speed, and we start to feel like the world has gone completely mad. But if we look closer, if we take the time to understand the underlying mechanics, we realize that everything is still governed by its own inherent laws. That it is merely an effect of perspective, a simple interplay of light and shadow. This understanding doesn't negate the reality of the event, but it offers us profound calm and much-needed clarity. It allows us to see the reality hidden behind the illusion and find order within the apparent chaos. And so it is in the cosmos. Behind the frightening and paradoxical display of the superluminal shadow lies nothing more than a simple, elegant geometry. So, as we conclude our nocturnal journey, we can confirm that a shadow truly can move faster than light. But this movement is nothing more than an illusion, a beautiful dance of geometry played out across cosmic distances. Since it transmits neither matter nor energy nor information, it poses no contradiction to the fundamental laws of physics. This paradox isn't an error in our theory, rather, it serves as its subtle and elegant confirmation. It highlights how crucial it is to clearly define the concepts we use. The movement of an object and the movement of a pattern are simply not the same thing. The universe continually reminds us of this by presenting us with endless new mysteries. And diving deep into the secrets of the cosmos to unravel them is perhaps one of the most profoundly tranquilizing endeavors one could ever imagine. So today we've seen how something as simple and commonplace as a shadow, when observed on a cosmic scale, transforms into a truly astonishing phenomenon, one that, at first glance, seems to shatter the most fundamental laws of physics. We understood that a shadow is not an object, but rather the absence of light. And it is precisely this characteristic that frees its movement, allowing the boundary between light and darkness to sweep across cosmic screens at speeds many times faster than the speed of light itself. We learned that this does not violate Einstein's postulates because such a shadow is utterly incapable of transmitting information. It is simply a stunning optical illusion, a type of phase velocity born from the geometry of vast interstellar spaces. This knowledge doesn't diminish the wonder. If anything, it makes the phenomenon even more elegant. Thank you for spending this time contemplating the mysteries of the universe with me. If this cosmic riddle helped you relax and spark some thought, please hit the like button and subscribe for more bedtime physics or sleep lectures. Make sure to click that notification bell so you don't miss our next journey. What other paradoxes of physics or space would you like us to explore in future videos? I look forward to reading your ideas in the comments below. Good night, and may your dreams be clear.